Hello and welcome to Thursday's edition of Cracking the Cryptic on a really big day for the channel. We're going to be taking a look at this puzzle on the screen, which is by Peter Venus, and Mark rates this one incredibly highly. He solved it yesterday, I believe, on Logic Masters Germany, and he sent it to me with the instruction that I needed to make a good video and I needed to solve it because it needs to be seen. And I think that's because these yellow boxes are so-called miracle squares. Now, what is a miracle square, I hear you asking? Well, I'm not exactly sure, but anyway, that will all become clear when I read the instructions in just a second. But before I do that, I am delighted to tell you that Marge, with the help of Cracking the Cryptic viewers, has found her inheritance. So I know many of you will have been following this story over the last week or so, but basically Marge received this puzzle in her late grandfather's will, and she solved it with the help of Cracking the Cryptic followers, and it led on a whole puzzle hunt which was completed last night. Now, this was all the work of Scott Strossal and Jake Whitkey, who deserve all sorts of props for keeping so many of you entranced these last few days. And it was all a big setup, to be honest, because the inheritance turned out not to be a Ferrari. It wasn't anything as facile as money, but it was, if you finished it all correctly, it was a plain old URL, which led to the first pilot edition of a brand new Cracking the Cryptic podcast. So many of the epic solvers over on Discord got to listen to that yesterday, and this morning we released it on the channel. So we are not at all sure that the world needs a Cracking the Cryptic podcast. We were persuaded to do this. To be honest, we've been charmed so far by the comments. So maybe it is a real thing, and maybe it's not quite as balmy as it seems to us. But do give it a listen. And if you do enjoy it, we will try and make more episodes, and we will make those episodes available on the normal sort of podcast outlets rather than just putting them up on the YouTube channel itself. Yeah, and obviously thanks so much to Scott and Jake. The work they did to create the hunt was magnificent, and we will certainly listen to any appeals if people want to. Maybe we should do a video, or we'll get one of them to do a video on the whole hunt, because it was marvellous, and it did lead to some very interesting video footage of the late grandfather, very elderly gentleman who did remind me a bit of Mark. Anyway, the other thing to mention is it's very nearly the 1st of May, and on the 1st of May we have an amazing treat for anyone who's a patron of the channel over on Patreon. Matthias Martinka has created it's just a stunning Sudoku puzzle hunt, and it contains exceptional puzzles. There's a whole range of difficulties, and the first correct solution we receive will receive some new merch. So there's a little bit of an incentive for any of you who are competitive out there. And if you're not competitive but you do manage to finish it, send us the solution at the end, and we will read your name out on the channel because you will deserve it. So that's coming just in a couple of days' time. And with all that said, let's get on to Peter's puzzle, and I will tell you about these what's it called? Miracle squares that we have to learn about in these positions. These yellow squares are miracle squares, and apparently this is something that mathematicians in particular are going to just be, well, they're going to find something very enjoyable about these squares. I'll read you the rules. Normal Sudoku rules apply. Digits separated by an X sum to 10, and digits separated by a V sum to 5. So you can see there's some dominoes in the grid where there are V's between them, so those two squares have to sum to 5, these have to sum to 10. Now, here's the bit about the miracle squares. For any pair of orthogonally adjacent cells where both cells are coloured yellow, so that would be, for example, those two cells, the digits cannot add to 5 or 10. The digits cannot be consecutive, so they cannot have a difference of 1. The digits cannot have a ratio of 1 to 2, so one of the digits cannot be double the other. And that's all we're told about them. But apparently, per Peter, and a note he wrote, rather like Fermat's last theorem, he said that there is no bifurcation required to find out how these boxes work, and there is a beautiful logical proof, which he wrote in the margin of his work, but no, he didn't write it in the margin of his workbook, but he says that there is a beautiful logical proof that shows exactly how these miracle squares work, and that is going to be our task. Now, what I will say is that because I read these instructions yesterday, my brain has percolated on this overnight, and I have had a thought about how I might get some traction on these squares. So that's where I'm going to start in a moment. Do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. Now I'll tell you my thought for what it's worth. And my thought is that the most restricted digit in one of these miracle squares is the digit 4. Now, why on earth do I think 4 is restricted more than any other digit? Well, it's a bit of experience with Kropki Sudoku. So, if you're familiar with Kropki Sudoku, you'll know that 4 is one of the few digits that can be in 2 black Kropki dot relationships. In other words, there is a number between the digits 1 to 9 that is double the number 4. That's a knowledge bomb for you. It's the number 8. There is also a number between the digits 1 and 9 that is half of 4, and that's 2. So the 4 cannot go next to a 2 or an 8 in this box. Now, there are very few other digits. There's in fact only one other digit that is restricted in that way, and that's the digit 2. So 2 obviously can be in a relationship with 4 and 1. It's half of 4 and it's double 1. But think about this digit here, this 1. This one would also be ruled out from being next to 2 by the fact it's consecutive with 2. Whereas, for the 4, the 3 and the 5 are, sort of have to be ruled out by the consecutive rule. They are not also ruled out by the ratio of 1 to 2 rule. So I think that 4, sort of uniquely in the panoply of digits between 1 to 9, is subject to a lot of restriction, and moreover we can also say that 4 can't be next to 1 because 1 plus 4 equals 5, and it can't be next to 6 because 4 plus 6 equals 10. So in fact, for every type of relationship that exists in a miracle square, the digit 4 is restricted because it can't be next to, let's just work this out, so it can't be next to 1, it can't be next to 2, it can't be next to 3 because of the consecutive, it can't be next to itself, it can't be next to 5, it can't be next to 6 because of the 4 plus 6 is 10, and it can't be next to 8 because 8 is double 4. So the only digits that 4 can be next to are 7 and 9, and that means 4 is not in the middle of this box because there are 4 orthogonally connected cells with this square here. So 4, in fact, has to be in a corner. That's right, isn't it? 4 can only be next to 7 and 9. So this is right. This is definitely the start of this, isn't it? Because now, if 4 can only be next to 7 and 9, where are we putting the 4 in the box? And we don't know exactly where we put it, but we do know it's in one of 4 squares, because if you can only put the 4 next to a 7 and a 9, it must be in one of the 4 corner squares. Because otherwise it will be, if we tried to put 4 here, for example, there would have to be, we couldn't put 7 and 9 in those 3 squares. So let's sort of tentatively pencil a 4 in here, and then 4 will be next to 7 and 9. And that's going to affect the middle square, look. Oh, good grief, this is absolutely lovely because, well, not only can this square definitely not be 8, because 8's most certainly it's consecutive with 7 and 9, in fact, but this square can't be 1, because then it will be next to whichever one of these is a 9, and 1 plus 9 is a knowledge bomb, equals 10, and it can't be 3, because 3 plus 7 equals 10. So what can that square be? That square can't be 1 or can it be 2? Maybe. maybe it can be 2. It can't be 3. It can't be 4. 4's already in the corner. It's... Can it be 5? It probably is 5, actually, thinking about it, because in a magic square, the central digit is a 5. If you're tasked with the... or you're set the task of creating a magic square where every row and column and diagonal of a 3x3 box add up to the same number using the digits 1 to 9, you'll always have to put 5 in the middle. Now, and 5 in this version of the miracle square is also very flexible, isn't it? Because 5 can't be in a relationship with another digit that adds to 5, because you can't put 0 in. And it can't be in a relationship with a digit that adds to 10, because then you'd have to go double 5. So it probably is 5 in the middle, but we don't know that for sure. What about 6 here? You can't put 6 here because it'll be consecutive with 7. And you can't put 8 here. So this digit is 2 or 5. So what we'll do is we'll rule out 2. So now, if there's a 2 here, what can't that? That can't go next to 1 or 3. Oh, or 8. Good grief, right. Wow, right, okay. So if there is a 2 in the middle of a miracle square, you can't put 8 next to it because 8 plus 2 equals 10. You can't put 1 or 3 next to it because they're consecutive with it. So the 1, 3 and the 8 would have to hide in the corners. Let's just have a look at that. And then we would have to put 5 and 6 into those squares, which... hang on a minute. Why is this wrong? It's wrong because we can... In fact, 8 would have to go... You can't put 8 in either of those squares because 8 is always going to then be next to a 7 or a 9 and it's consecutive with both, so 8 would go here. I'm not actually sure that fails, to be honest. Ah, okay. Maybe I'm wrong, actually, then. Maybe this digit can't be 5. Let's have a look at 5. The interesting thing about 5 is not actually the 5. The interesting thing about 5 is the 2 that we were just talking about, because now, if those 4 digits are 4, 5, 7 and 9, these 5 digits firstly have to include that 2, but secondly we have to hide the 2 from the 1, 3 and the 8. So the 2 would have to go into one of those 2 squares. Because in any other position, if you try and put the 2 in any of those positions, it's obviously consecutive with, if you try to put the 2 here, you can't put 1, 3 and 8 into that domino. One of those digits would go there and break the puzzle. So 2 would have to be in one of those squares. Let's just pencil that in. So if 2 was here, you'd have to put the 1, the 3 and the 8 there. And it breaks. That's amazing. So the 6 then has to go here. You have to keep the 1, 3 and the 8 away from the 2. The 6 would have to go here and it will be consecutive with the 5. And that obviously works exactly the same way if we try to hide the 2 in that corner. It's not going to help us. You then still got to put the 6 here. It's still going to be next to the 5, and this is wrong. And wrong in this case is good. So now that is a 2, I think, which means those 2 squares are also 2s. So in a miracle square, you have to put 2 in the central cell. And that, right, and let's carry on with the logic. So now we know those, we know those squares have to be, 1, 3 and 8 have to be kept apart from the 2. We know those 2 could never be 8 because they are going to be consecutive with the 7 and the 9. So that places the 8 in that square. Now what I'm not doing is putting these squares around the edge in. I'm not making them large digits because I don't know the order of these. I've put the 4 here, but it just as easily could be in one of the other 4 corner squares. So what we're trying to do is to establish the relationship between these ring squares. And and we'll see if we can actually get to the bottom of that. So we've got 5 and 6 here. Right, okay. And now it gets tricky, doesn't it? Because we don't know which of these is 7 and which of these is 9, but we do know that whichever way round it goes, it fixes the whole thing. So let's, for example, if we thought that if we do it this way round, just because we have to do it one way round to show this, if this is a 9, you can't put the 1 there. So you'd have to put the 3 there. Then this square would become the 1. The 1 can sit next to the 7, so that's fine. Oh, this is just beautiful. And then the 3 disambiguates the order of the 5 and the 6, because 6, of course, is double 3 and therefore can't be next to it. So you'd have to go like that. So if you start with 4, 9, this is a forced pattern round the perimeter of the miracle square. So ignoring rotations and reflections, this is the only way that you can construct a miracle square. That is an extraordinary thing, actually. Okay, I'm going to be interested in the comments, assuming I can solve this puzzle, because that feels like some sort of weird discovery. Now, what we're going to have to do, though, is we do not know what the ordering is. We don't know if it starts 4, 9, or if the 4, 9 goes that way round. So we don't know if it goes clockwise or anti-clockwise, and we don't know where it starts. We just know the approximate order of the digits, and we're going to have to. So hopefully, all of this gubbins in the grid is going to tell us the ordering. And somehow, I'm also going to have to remember this order, because otherwise, as I fill it in, it's all going to get very confusing. What I will try and remember to do when I edit the video is to put the magic or the miracle square over the instructions or something, so at least you guys will know what's going on. I can see, look, right, 4 is always opposite 8. Let's remember that. 1 is opposite 3. 6 is opposite 9. 5 is opposite 7. I can remember that, can't I? 1 and 3, 4 and 8, 6 and 9, 5 and 7. Right, that's what we're going to do. I'll also remember, because it's the World Snooker Championship, that 147 appears on one side of this, although it's not in the order 147, it's in the order 174, which of course could be 471 as well. This domino has to be 1 or 4, because it can't be 2, 3, look, because the 2 is already there. So in fact, get a digit. Oh, I could have got this a while ago. Look, this domino here has to be a 2, 3 domino, and the 2 just gives us the order. So that's a 2, and that's a 3, and that's a 7, because those two squares add up to 10. Now, does that tell us? Oh, good grief! Right. So now this is definitely wrong. Well, no, the miracle square is correct, but it's definitely not in this orientation, because this 3 is telling us the 3, which is in a corner, is in one of those two corners, bobbins. And the 3 is opposite a 1, isn't it? That's what we've learned from the sort of small digits. So the 1 is actually in one of those squares, which means there's a 1 down here by Sudoku. There's a 3 in one of these squares by Sudoku. I'm not sure if I can do anything more. I can see 7 isn't in this square, but that means 7 is in one of 3 positions. Oh dear. Oh, 9, look, now can't be there anymore. Oh, good, this is going to get so complicated. 9 can't be here, because it would then be next to a 1. This is, yeah. I'm not going to take out the small digits yet, though, because I don't feel like I've remembered the square well enough. Maybe we can get some more Sudoku, and that will help us. So we've got 1, 4 there, look. That square's a 6 or a 9 using the X relationship. That's a 1, 4 pair because of the 2. Oh, yes, yes, yes. Now, look at this domino. This is absolutely huge because, and not just because, this is a 3-7. In fact, that's the least attractive thing about this domino. Why is it 3-7? Well, we know it adds to 10. It's not 1-9, it's not 2-8, and it's not 4-6, so it must be 3-7. But now we know the orientation of the 7 in this box. It's vertical, because it can't be in those two squares. And we know that 7 goes opposite of 5. So these two squares and these two squares, we now approximately know they are a 5-7 pair. These are a 6-9 pair. Oh, we've done it, because now we know the 1 is in one of those squares, because the 1 has to be opposite the 3, and you can't put 1 next to 9. So this square is a 6, and that square is a 9. And now the 4 can't be next to the 6 because it would add to 10. So those two squares now are known to be a 3-4 pair. And that means those two squares are known, I think, to be a 1-8 pair. And we have a 9 here by Sudoku. And I was about to say we have liftoff. We have solved Venus's last theorem. And we have provided an elegant proof that would fit in the margin of this YouTube video. 2, 3, 4, 5, 6, and 8 into those squares. And 1, 2, 7 at the bottom. Oh, 1, 2, 7 at the bottom. And look, there's a 1 and a 2 in that row, so we can actually do some Sudoku for a change. 7s go into these squares. Or that square. This is a 1-2 pair. And now, you know what I'm going to do, don't you? I'm using this 7 on this one. Because this is a miracle square, and we now know those two aren't 7 in that one. So the 7 is vertical in this miracle square, and the 7 and the 5 are therefore in the vertical plane, which means the 6 and the 9 are in the horizontal plane, which means that I still don't know how the corners work, do I? I'm very bad at this indeed. I feel like I probably do or should know how the corners work. Maybe I don't. I'm not sure. I'm not sure whether I do or I don't. Let's look at this row though, because we've got lots of stuff we know about this. In fact, I'm going to change these pencil marks over because they're going to bug people otherwise, because they're already bugging me. We can do them like that. So now this row, look, has got to have 3, 5, and 8 in it. Well, that square's a 5 by the power of our old friend Sudoku. So those are a 3-8 pair. That's going to be nice for this one. So let's look at that. This square now has got to be 7 or 2. Right, okay. Well, it doesn't actually reveal the secrets of the universe, does it? What are those squares? 3, 6, and 8. What are these squares? They are 9 and 4, I think. Okay, so that's... I'm getting a bit worried actually, because if you actually look at the grid, I don't know anything about the middle miracle square, because this 3 is absolutely hopeless. Because 3 goes in a corner, so this 3 is not restricting it. This 7 is very nearly hopeless, because we know the 7 is in one of those squares, therefore we don't know its orientation. 2 has to be in one of these two squares. So, and we've basically, unless I've missed something, we've used all of these XVs apart from this one. I don't see, oh, that one as well. Okay, yeah, this one is either 1, 9 or 4, 6, because it can't be 3, 7, it can't be 2, 8. It's nearly a triple or a quadruple, but not quite. Surely I now know. Do I know the whole of this? Is that the point? Can I go further than I've gone here and actually disambiguate the whole shebang? I probably can, I'm just not spotting how to do it. Yeah, I'm sure that once you know the order of the 6 and the 9, you must be able to get the order of the 5 and the 7, because there was only, it was always a string of digits. Oh dear, why can't I remember how that worked? 1s were opposite 3s, 4s were opposite 8s. I can't remember how it worked in the middle. Oh! I can't remember. I could reinvent the wheel and do it again, couldn't I? Let me try and do something else first. Maybe there's some other trick we can use. Maybe that domino. No. Bobbins. Or this one. We've got something similar to what we've got up here, down here, look. Right, okay, I can do a trick. There was a 147 on one side, wasn't there? Because I remember from the snooker thing. Well, I can't put a 7 there then, because if there is a 7 and a 1 in that triple, though both of these squares would have to equal 2, which is impossible. So I don't think that can be a 7. I think that has to be a 5, and that has to be a 7. Which means there's definitely a 1 and a 4 down here now, which is nice. That gets me off and running again. I've now got a 2 and a 1 there. Now these squares have got to be 3 and 8, which is nice. That gets me a 6 over there, which gets me a 9 and a now we might be cooking with gas, actually. Suddenly I'm getting digits. This is not 6. So, have we just done something profound or not? Perhaps not. This square, yeah. Where does 2 go in row 7 of the grid? It can only go in that square, which gets me an 8 here. Now this square has to be the missing digit in this row, which is a 7. This 7 is lovely, because that rules the 7 out of those 2 squares, which means that's a 5-7 pair, because we know that 5s and 7s are opposite one another. That's not 5 anymore. This 7 gets me a 7 and a 3 at the top of the grid. Still don't know where the 3 goes down here. Those squares have got to be 3, 5 and 6, which is going to be nice, because that resolves this 3-8 pair. And okay, and we reach this position, do we? Okay, this 8 is nice. That's fixing the 5 here. Oh, I didn't mean to do that at all. That's the new loop drawing part of the software. This square is a 5. This square is an 8. That gets me an 8 and a 3 down here. Now this is much bigger, because I cannot put 3 next to 6, or it would be in a problem relationship. 6 goes here. I can't put 1 together with 9, or that would be adding up to 10. So this one we've done. And this 1 actually gives me the 1 and the 4 at the top. 8 by Sudoku's got to go in this square, which means this domino here, you can see it actually from that 1 there. This has got to be 4 and 6, which means those 2 squares are 3 and 9. And we pause for breath and see where we're. These squares are a 6-9 pair, because we know that 6s and 9s are the other sort of part of the cross. That square's not 6. Actually, that square is 5, therefore there's a 3 at the top of the grid, which means we now know those 2 squares are 1 and... Oh, I was about to say 1 and 8. I think they are 1 and 8, and I was about to get very concerned, but because of this deadly pattern. But maybe it's resolved by this domino here. So this has got to be 2. Ah, yeah, here we go. This has got to be 2 or 9, and it can't be 9. Thank goodness for that. So that resolves the deadly pattern very smoothly. And this should be lovely, because now surely I know how this should look. Because I know that 1, 4 and 7 go together on one wing of it, don't I? So this should be 7. You can see it down here. I don't think it's worth reproving. I think we could do if we wanted to, but we don't need to. Now that 3 is fixing the 3 and the 9. That's placing a 9 here. These two squares are 4 and 6, which I don't know the order of. But that means those two squares are 2 and 7, which I also don't know the order of. And those two squares are 5 and 6, which somehow I also don't know the order of. That was, the puzzle is mocking me here. Okay, but that was still progress of a sort, wasn't it? So now we can see 8. 8 in box 5 is forced to be there. And 8 is never next to 7. 8 is always next to 5. So now we know the order of this one. 8, 5 always goes with 3. You can't put a 6 with a 3, so it must look like that. You can't put a 1 with a 9, so it must look like that. That looks gorgeous, because now we can do those squares. We can do that square. 6, 8 pair is resolved by the 8 on the right. 8 and 6 go in. Ah, yeah, okay. 4 and 6 is now resolved in this box. And surely, yeah, there we go. 4, 6, 6, 3, 6, 5, because of this 6 down here. Oh, so maybe I was wrong when I alleged that this wasn't resolved. I'm not sure. And then 5 and 7 go into those squares, which we can do. That fixes the 7 and the 2. That fixes the 2 in this box. You see we need 1, 3 and 9 here, and we can just fill it in. 3, 1, 9. Click tick. That is a beautiful, beautiful puzzle. My goodness me. How on earth, Peter, did you discover that there is only one, ignoring isomorphs, there is only one way of filling in a miracle square? That is some discovery. Loved it. Absolutely loved it. And it was a good puzzle as well. Let me know in the comments what you think. Let me know if you enjoy the podcast, of course. And we'll see you later for another edition of Cracking the Cryptic. Want you near me now, want you near me.